The black hole is not a grave, it is a trick of the light. We look at that dark circle and see a silent, eternal prison. But deep inside, the star is not dead. It is actually bouncing. It is currently exploding with the force of 1 billion suns, but gravity has trapped that explosion in a cage of frozen time. We need to solve this mystery because the old math claims the universe is broken, that it destroys information. But the truth reveals a cosmos that doesn't delete its history. It recycles it. In this video, we replace the bottomless pit with a solid object and meet the secret hiding in the dark, the Planck star. Let's begin. Chapter 1. The Impossible Error. Everything you have been told about black holes might be wrong. For decades, we have stared at these dark monsters of the universe with a mixture of fear and awe. We have built entire movies, written thousands of books, and dedicated our lives to understanding them. We tell ourselves that we know what lurks in the center of that darkness. We tell our children that gravity becomes so strong that it rips a hole in the fabric of reality. We tell ourselves that at the bottom of the pit lies a singularity. But I am here to tell you that the singularity is not a fact. It is a lie. It is a story we tell ourselves to cover up a terrifying truth. We have no idea what is actually going on down there. The most famous object in our universe is based on a mistake. Stop for a moment and imagine the picture we all have in our heads. You see the glowing ring of fire, the event horizon. That is the point of no return. Once you cross that line, you are falling. You are falling toward the center. And what do traditional physics tell us is waiting for you? They tell you that you are falling toward a point of infinite density. This is the standard definition of a black hole. A massive star that has collapsed down, smaller and smaller, until it occupies zero space, 0 dimensions, a single point with no width, no height and no depth, but containing all the mass of a sun. This concept is called the singularity. It is the defining feature of a black hole. It is what makes them black. It is what makes them holes. But there is a massive problem. A problem that keeps physicists awake at night, sweating in the dark. The problem is the word infinite. You see, in the real world, infinity does not exist. You can have a lot of something. You can have 1 billion tons of rock. You can have 1 trillion stars. You can have numbers so big they break your brain. But you cannot have infinity. Infinity is not a number. You cannot count to it. You cannot measure it. In the world of mathematics and physics, infinity serves a very specific purpose. It is not an answer. It is an error message. Think about your calculator. If you try to divide a number by 0, what happens? Does the calculator give you an answer? Does it tell you a deep secret about the universe? No. It says error. It crashes. It tells you that you have asked a question that the system cannot handle. When Einstein's equations of general relativity predict a singularity, they are effectively dividing by 0. They are telling us that the density at the center becomes infinite. They are telling us the heat becomes infinite. They are telling us that gravity becomes infinite. When a physicist sees infinity in their math, they don't celebrate. They panic, because it means the theory has broken. It means the equations have stopped describing reality and started speaking nonsense. So why do we accept the singularity? Why is it in every textbook? Why is it in every documentary? Because for the last 100 years, we didn't have a better alternative. We assumed that because gravity is a relentless crushing force, nothing could stop it. We assumed that once a star starts collapsing, it must collapse forever. We imagined a bottomless pit in the fabric of the cosmos. We accepted the error message as the truth. We looked at the blue screen of death on the computer of the universe and assumed that was just how the universe looked. But deep down, every serious scientist knows that nature does not do singularities. Nature does not do infinite points. Nature makes sense. If you take a physical object like a star and you squeeze it, it gets smaller. If you squeeze a sponge, it gets smaller. If you squeeze a planet, it gets smaller. But can you squeeze it until it disappears? Can you squeeze it until it has no size at all, yet still weighs the same? Impossible. Everything in our universe has a limit. Everything has a bottom. If you zoom in on a piece of paper, you eventually see fibers. Zoom in on the fibers, you see cells. Zoom in on the cells, you see atoms. There is always a structure. There is always something. The idea that a black hole has nothing at its center is an insult to the complexity of the universe. This brings us to the most explosive realization in modern astrophysics. If the center of a black hole is not a singularity, then what is it? If the math of the singularity is actually just an error code, what is the reality hiding behind that error? If the star does not vanish into a mathematical point, it must go somewhere. It must turn into something. Imagine the collapse again. The massive star is dying. Gravity is winning. The iron core collapses inward at thousands of miles per second. It crushes down past the size of the Earth. It crushes down past the size of a city. It crushes down past the size of a grapefruit. According to the old story, this crushing never stops. It goes to infinity. But what if it stops? What if there is a flaw to the universe? What if, deep inside that darkness, shielded from our eyes by the event horizon, the star hits a limit? We are standing on the edge of a new scientific revolution. A revolution that suggests the scariest monsters in the universe are actually disguise artists. We are starting to realize that the bottomless pit has a bottom. We are starting to realize that the center of a black hole is not empty. It is not a void. It is not a tear in the cosmos. It is a solid object. This is the secret that physics has been whispering about for the last few years. There is a theory hidden in the complex math of quantum mechanics that predicts something beautiful and strange. It predicts that when the star collapses, it doesn't die. It transforms. It becomes something that defies all our common sense. It becomes a Planck star. Imagine an object so dense that a single teaspoon of it would weigh as much as the moon. Imagine an object effectively frozen in time. This isn't just a dense ball of matter, it is a new state of reality. The impossible error of the singularity was blinding us to this possibility. We were so obsessed with the idea of infinity that we forgot to look for the finite, solid truth. The reason you have never heard of the Planck star is that it sounds too crazy to be true. It sounds like science fiction. It suggests that inside every black hole you see in the night sky, there is a tiny, hidden heart beating in the darkness. It suggests that the black hole is not a tomb, but an EGG. The concept of the singularity tells you that information is destroyed. It tells you that the past is erased. It tells you that if you fall in, you cease to exist in any meaningful way. It is a concept of death. But the Planck star? The Planck star is a concept of life. It suggests that the matter survives. It suggests that the star is still there, waiting. We have to stop trusting the broken math of the past. We have to stop accepting infinity as an answer. Because when you remove the error, you reveal the mystery. And the mystery is so much more thrilling than the mistake. If there is a solid star inside that hole, it changes everything. It changes how we view time. It changes how we view the Big Bang. It changes how we view our own existence. So I want you to erase the picture of the singularity from your mind. Delete the tiny infinite dot. It doesn't exist. Instead, I want you to picture something else. Picture a star that has been crushed by gravity, screaming as it shrinks, pushing against the very fabric of space and time until it hits the absolute limit of nature. It hits the basement of reality. And there, in the deepest dark, it waits. This is not just a theory about rocks and gas. This is a battle between two laws of physics. On one side, you have gravity, the crusher, the destroyer, the force that wants to squeeze everything into nothing. On the other side, you have quantum mechanics, the rule book of the atoms, the force that says, "You shall not pass." For 100 years, we thought gravity won the fight inside a black hole. We thought gravity crushed quantum mechanics into submission. But the Planck star theory says no. It says quantum mechanics fights back. It says that at the very last second, just before the star vanishes forever, the universe puts up a shield. The singularity is the impossible error. It is the lazy answer. It is the placeholder we used until we were smart enough to find the real answer, and now we think we have found it. The black hole is not a hole at all. It is a hiding place. It is a vault, and inside that vault sits the Planck star. But if there is a star inside, why can't we see it? Why does it look black? And most importantly, if the star didn't disappear, what is it doing right now? Is it just sitting there? Or is it preparing to do something terrifying? The answer to that question requires us to shatter our understanding of time itself. Because the star isn't just sitting there. The star is actually exploding. But it is exploding in a way that our human brains are not built to comprehend. We are about to enter the strange world of loop quantum gravity. We are about to look past the error message and see the code of the universe itself. Forget the singularity. The singularity is dead. Long live the Planck star. But to understand it, we first have to understand why the universe has a pixel size. We have to understand the grid. We have to go deeper than we have ever gone before. Are you ready to see what is really inside the dark? Because once you see it, You will never look at the night sky the same way again. The monster is not a monster. It is a ghost of a star that refuses to die. And its story is just beginning. Chapter 2. The Villain, the Paradox. Every great story needs a villain. Usually the villain is a person, a monster, or a disaster. But in the story of the universe, the villain is something much more terrifying. The villain is a paradox. It is a glitch in the logic of reality that threatens to tear down everything we think we know about the world. To understand this villain, we have to look at the two greatest heroes of modern science. On one side, we have Albert Einstein and his theory of general relativity. On the other side, we have the chaotic, rebellious world of quantum mechanics. These are the two rule books that govern our universe. They are both brilliant. They are both proven to be true in thousands of experiments. But there is a dirty secret that physicists don't often talk about at dinner parties. These two rule books hate each other. They do not get along. In fact, they are practically at WAR. And the battlefield where they meet to fight to the death is the center of a black hole. Let's start with the first contender, gravity. When Einstein rewrote the laws of physics, he described gravity not as a force, but as a shape. He told us that space and time are like a flexible fabric. If you put a heavy object on the fabric, it bends, it curves. This is general relativity. It is elegant, smooth, and beautiful. It works perfectly for big things, planets, stars, galaxies. According to Einstein, gravity is a relentless, crushing force. It is the ultimate tyrant. It wants to pull everything together. It wants to squeeze matter until it is tight and dense. And inside a black hole, gravity goes completely insane. It becomes so strong that it bends the fabric of space into a bottomless pit. Einstein's math is very clear about what happens at the bottom of that pit. It says that gravity wins. It says the star gets crushed down, smaller and smaller, effortlessly shrinking past the size of an atom, past the size of a proton, all the way down to zero. Gravity demands a singularity. It demands that the star disappears into an infinitely small point. But now we have to introduce the challenger, the underdog, the rebel. This is the world of quantum mechanics. This is the rule book for the tiny things, atoms, electrons and photons. And if gravity is smooth and predictable, quantum mechanics is a rave party. It is chaotic, jittery, and impossible to pin down. In the quantum world, nothing stands still. Particles are popping in and out of existence, vibrating with energy, refusing to sit quietly in one place. And there is one golden rule in quantum mechanics that cannot be broken. It is the shield that protects the universe from collapsing. It is called the Heisenberg uncertainty principle. This principle sounds complicated, but it is actually very simple. Nature hates being pinned down. Imagine you have a hyperactive child in a room. If you let them run around the whole house, they are relatively calm. But if you try to lock them in a small room, they start bouncing off the walls. If you try to lock them in a closet, they bang on the door. If you try to hold them tight in your arms so they cannot move an inch, they will scream and fight with everything they have. Particles are exactly the same. They have a property called position, where they are, and momentum, how fast they are moving. The Heisenberg uncertainty principle says you cannot know both perfectly. If you try to squeeze a particle into a tiny specific location, its momentum goes wild. It starts moving frantically. It starts vibrating with massive amounts of energy. This creates a force called quantum pressure. It is a pushback against being squeezed. So now we have the setup for the ultimate cosmic showdown. This is the paradox. This is the villain. Picture the collapsing star again. It is falling into the black hole. Gravity, the tyrant, is crushing it down. It squeezes the star into a ball the size of a city. Gravity says, smaller? It squeezes it to the size of a grapefruit. Gravity says, smaller. It squeezes it to the size of a sand grain. Up until this point, gravity is winning. But suddenly the star gets so small that it enters the realm of the tiny. It enters the territory of quantum mechanics. Now the atoms are being forced into a space that is too small for them. According to the Heisenberg uncertainty principle, the particles start to panic. They get claustrophobic. Gravity is trying to pin them down to a single point, but the particles refuse to be pinned. They start vibrating faster and faster. They start pushing back with incredible force. Gravity pushes in. Quantum mechanics pushes out. It is the classic case of an unstoppable force meeting an immovable object. Einstein's general relativity looks at this situation and screams, "Crush it! There's nothing that can stop gravity. Make it a singularity. Make it zero." But quantum mechanics looks at the situation and screams back, "No! You cannot have zero size. You cannot pin me down. I need space to move. I will fight you forever." This is the crisis of modern physics. We have two theories that are supposed to describe reality, and in this one specific spot, the center of a black hole, they give us two completely opposite answers. Einstein predicts a bottomless pit. Quantum mechanics predicts a hard floor. They cannot both be right. If Einstein is right, then quantum mechanics is broken. If quantum mechanics is right, then Einstein is wrong. You cannot have a singularity and the uncertainty principle in the same room. It is a logical contradiction. It is a paradox. Why does this matter? Why should you care about a fight between math equations? Because this paradox means that our understanding of the universe is incomplete. It means there is a massive hole in our knowledge. If our science cannot explain what happens when a star dies, then our science is flawed. We are missing a piece of the puzzle. The singularity is the result of Einstein ignoring the rebellion of the particles. But the particles are real. You are made of them. The phone or computer you are watching this on is made of them. You cannot just ignore the laws of the universe because they are inconvenient for your math. The tension is building. The star is shrinking. The pressure is rising to levels we cannot comprehend. Gravity is pushing down with the weight of 1 billion suns. The particles are screaming, vibrating, pushing back with the fundamental energy of existence. Something has to give. Something has to break. Does the star get crushed into nothingness, violating the laws of the quantum world? Or does the star find a way to stop the collapse, violating the laws of gravity? For a long time, we thought gravity was the winner. We thought the villainy of the paradox was resolved by simply deleting the star from existence. But there is a third option, a secret option. What if the floor of the universe is harder than we thought? What if there is a limit to how small space itself can get? The paradox exists because we assume space is smooth. We assume you can zoom in forever. Einstein assumed space was like a smooth sheet. But what if space isn't smooth? What if space is pixelated? If space is made of pixels, then gravity loses its power to crush things to zero. You cannot crush something smaller than 1 pixel. If this is true, then the villain, the paradox, is defeated. The two theories can make peace, but to understand how, we have to look at the fabric of the universe through a microscope that doesn't exist yet. We have to see the grains of reality. The battle lines are drawn. Gravity is pushing in. Quantum mechanics is pushing out. The star is caught in the middle, trapped in the most violent embrace in the cosmos. In the next chapter, we are going to reveal the hero that saves us from this paradox. We are going to reveal the grid. We are going to see what happens when the unstoppable force hits the absolute fundamental limit of the universe. The star isn't going to vanish. It's going to hit the ground. And when something hits the ground at that speed, there is only one thing that can happen. It doesn't die. It bounces. But before it bounces, it has to become something strange. It has to become the solution to the riddle. The paradox tells us we have a problem. The Planck star is the answer. But to build a Planck star, we first need to understand the building blocks of space itself. We need to stop thinking of space as nothing and start thinking of it as something. The paradox is scary because it suggests we are blind. But the solution is beautiful. The solution suggests that the universe has a safety mechanism built into its very code. A safety mechanism that prevents the catastrophe of the singularity. The villain of our story is about to be defeated by the smallest hero imaginable, a hero the size of a single Planck length. Get ready, we are about to zoom in. We are about to go smaller than atoms, smaller than protons. We are going to the place where geometry itself is born. The paradox is the lock. Loop quantum gravity is the key, and we are about to turn it. Chapter 3. The Pixelated Universe. We have reached the breaking point. In our story, we left the massive star collapsing into the dark heart of the black hole. We left the laws of physics screaming at each other. Gravity wants to crush the star into nothingness. Quantum mechanics is fighting to keep it alive. It seems like a hopeless battle. It seems like the paradox is going to win. But just when all hope seems lost, just when the math is about to break and give us that terrifying error message of the singularity, a new hero steps onto the stage. This hero is not a person. It is not a machine. It is a revolutionary idea. It is a new way of seeing reality that completely shatters the illusion we have lived with our entire lives. To save the star and to save our understanding of the universe, we have to stop looking at the objects in space and start looking at space itself. Look around you right now. Look at the air in front of your face. Look at the empty space between you and the screen. What do you see? You see nothing. You see emptiness. You see a void. Our intuition tells us that space is just a container. It is a smooth, continuous stage where the drama of the universe happens. We imagine space is like a vast empty ocean, and stars and planets are just fish swimming in it. We imagine that if you zoom in on space, you will just find more space. You can divide it forever. You can cut a meter in half, then a centimeter, then a millimeter, then a nanometer, and you can keep cutting forever. This idea of smooth space is what Einstein used to build his theories. But this idea is the trap. This is the mistake that leads to the singularity. Because if space is smooth, you can shrink a star down to a pinpoint. But what if I told you that space is not smooth? What if I told you that the smoothness of the universe is a lie? To understand the hero that saves us, I want you to look at a photograph on your computer screen. From a distance, the face in the photo looks perfect. The skin is smooth, the curves are gentle, the colors blend perfectly into one another. It looks like continuous reality. But now, I want you to walk up to your monitor. Get close. Get uncomfortable close. Take a magnifying glass and press it against the glass. What happens to that smooth image? It falls apart. Suddenly, you don't see a face anymore. You see squares. You see red, green, and blue dots. You see pixels. The smoothness was an illusion created by your eyes because you were standing too far away. The reality of the digital image is that it is made of little blocks. And here is the crucial rule of the computer screen. You cannot have half a pixel. The pixel is the limit. It is the smallest possible unit of the picture. You can't zoom in past the pixel. Now hold on to your seat, because we are going to apply in this logic to the universe. There is a theory called loop quantum gravity. It is the rival to string theory, and it is the hero of our story. This theory makes a bold, terrifying, and beautiful claim. Space is just like that computer screen. Space is pixelated. If you were to zoom in on the fabric of reality, past the skin of your hand, past the cells, past the DNA, past the atoms, past the electrons, past the quarks, if you kept zooming in until you reached the absolute bottom of existence, you would see that space is not empty. You would see a structure. You would see tiny interlocking loops. You would see grains. We call these tiny units space atoms. This changes everything. This means that space is not a place where things happen. Space is a physical thing. It is made of stuff. Just like a beach is made of billions of grains of sand, the universe is made of trillions upon trillions of grains of space. This concept is known as quantum geometry. And just like the computer screen, there is a limit. There is a smallest possible size. In physics, we call this the Planck length. To give you an idea of how small this pixel of space is, imagine a proton. A proton is already unimaginably small. Now, imagine blowing that proton up until it is the size of the entire observable universe. If the proton were as big as the universe, the space pixel would be the size of a single speck of dust inside it. It is small beyond human comprehension, but it is not zero. It has a size. It takes up room. It is a definite hard chunk of reality. Why is this our hero? Why does this save the star? Because of the pixel limit. Remember the villain? The villain was the singularity. The villain was the idea that gravity crushes the star down to zero size. But if loop quantum gravity is true, then zero size does not exist in our universe. You cannot be smaller than 1 pixel. You cannot have a volume smaller than 1 grain of space. Imagine you are trying to pack clothes into a suitcase. You can fold them, squeeze them and sit on the suitcase to crush them down. But eventually you hit a limit. The clothes are made of atoms. You cannot squeeze the atoms into nothing. The suitcase eventually becomes full. It becomes solid. Now, picture the black hole again. The massive star is collapsing. Gravity is the person sitting on the suitcase, pushing down with infinite force. The star gets smaller and smaller. It crushes past the atoms. It crushes past the nuclei. But then, crash. The collapsing matter hits the grid. It hits the fundamental pixels of the universe. The star is trying to shrink to a point, but the space atoms say no. They say, "We are full. You cannot squeeze us any further." The collapse hits the hard floor of reality. The smooth slide into the bottomless pit vanishes, and instead the star slams into a concrete pavement made of quantum geometry. This moment is the turning point of the entire mystery. Because space is granular, the star does not disappear. It does not become a singularity. It does not break the math. It simply stops. It becomes a ball of matter that is packed as tightly as the laws of physics will allow. Every single gap has been squeezed out. The matter is sitting on top of the pixels of the universe, occupying the smallest possible volume allowed by nature. This resolves the paradox instantly. Einstein's equations said infinite density because they didn't know about the pixels. They were trying to divide by zero. But loop quantum gravity fixes the calculator. It puts a 1 in the denominator instead of a 0. The density is not infinite. It is just Planckian. It is mind-bogglingly high, but it is a real number. It is a finite amount. This realization is like waking up from a nightmare. The nightmare was the idea that the universe destroys information, that it has holes in it, that reality can just vanish. The hero, the pixelated universe, tells us that the universe is whole. It is solid. It is built on a foundation that cannot be broken. The space atoms are the unseen scaffolding that holds reality together. Without them, we fall into the abyss. With them, we have a floor to stand on. So, what happens to the star now? It has collapsed. It has been crushed. It has hit the floor. It is no longer a normal star. It is no longer made of hydrogen or helium or iron. It has been ground down into the most basic raw material of existence. It is a bundle of space and matter fused together in a way we can barely imagine. It is small, incredibly small. If the original star was the size of the sun, this new object is microscopic. But it contains all the power, all the mass, and all the history of the star that died. We have found the object hidden in the dark. We have identified the solid thing that replaces the singularity. The collapse has halted. The space atoms are holding the line. They are locking shields like a microscopic army, preventing the star from vanishing. But there is a catch, a massive energetic catch. When you run full speed into a wall, you don't just stop comfortably, you feel the impact, you feel the shock. Gravity has just slammed 1 trillion tons of matter into a brick wall of quantum pixels at the speed of light. That energy hasn't gone away. It is trapped. It is compressed. It is like a spring that has been coiled so tight it is vibrating with the power of a supernova. The space atoms have saved the star from death, but they have turned it into a bomb. We have solved the mystery of what is at the center. It is not a singularity. It is a cluster of these tiny space pixels holding the crushed star. But now we have a new question, a question that will lead us to the true identity of the Planck star. If you squeeze a spring all the way down until the coils touch, and then you let go, what happens? It doesn't stay compressed. It snaps back. The hero has done its job. It has provided the floor. But now we have to watch what happens when the star hits that floor. We are about to witness the greatest bounce in the history of the universe. The star isn't dead, it's just crouching, and it is about to jump. Next, we are going to look at this object, we are going to give it a name, we are going to visualize the birth of the Planck star. And we are going to realize that the end of the star was actually just a new beginning. The pixelated universe didn't just catch the star, it caught it for a reason. Get ready to meet the object that defies the darkness. Chapter 4. The birth of the Planck star. We are now effectively standing in the front row of the most violent event in the history of the cosmos. In the previous chapters, we stripped away the lies. We learned that the singularity is an error. We learned that space is not empty, but made of tiny hard grains called pixels. Now we are going to watch what happens when a dying star meets those pixels. We are going to witness the birth of an object so strange, so dense and so powerful that it defies every instinct we have about the physical world. We are about to meet the secret prisoner inside the black hole. Close your eyes and picture the collapse. A star millions of times heavier than our Earth has run out of fuel. It can no longer fight against gravity. In a fraction of a second, the iron core of the star implodes. The outer layers blow apart in a supernova, but we are not looking at the explosion. We are looking inward. We are following the core. It is falling in on itself at 25% the speed of light. It is screaming down a gravity well, expecting to fall forever. It crushes past the size of a planet. It crushes past the size of a moon. It crushes past the size of a mountain. The gravity is pushing with the weight of the entire universe, demanding that this matter disappear into nothingness. The star is terrified. It thinks it is about to die. It thinks it is about to be deleted from reality. But then it hits the floor. It does not hit a floor made of concrete. It does not hit a floor made of steel. It hits the quantum floor. It hits the fundamental grid of the universe that we discovered in the last chapter. The collapsing matter slams into the tiny space atoms that make up the fabric of reality. And for the first time in the history of the collapse, the motion stops. This is the moment the textbooks told you didn't exist. This is the moment the singularity was hiding from us. Imagine a high-speed train slamming into an invincible wall. Imagine a meteor hitting the bedrock of a planet. The violence of this impact is beyond human language. The matter wants to keep going down, but the space pixels say no. The loops of gravity lock together, they stiffen, they form a shield that is harder than diamond, harder than neutron stars, harder than anything in creation. The collapse is arrested instantly. The star has not disappeared. It has not vanished into a magic hole. It has been forged. In that split second of impact, the matter is transformed. It is no longer made of atoms. It is no longer made of neutrons. The pressure is so high that the very identity of the matter is crushed out of it. It becomes a pure, vibrating state of energy and geometry. It is packed together at the absolute maximum density allowed by the laws of physics. We have a name for this limit. We call it Planck density. To understand what Planck density feels like, you have to break your brain a little bit. We think of lead or gold as heavy. We think of the core of the Earth as dense. But Planck density is in a league of its own. Imagine taking the entire ocean, every drop of water on Earth, and squeezing it into a thimble. That is not even close. Imagine taking the entire Earth, every mountain, every city, every rock, and squeezing it into a sugar cube. That is still not even close. To reach Planck density, you have to take the mass of the entire universe and squeeze it into a single atomic nucleus. That is the level of tightness we are talking about. It is the end of the line. It is the game over screen for compression. You cannot pack nature any tighter than this. So the star is now sitting there. It has hit the floor. It is compressed to the ultimate limit. It is vibrating with the shock of the crash. And this new object needs a name. It is not a singularity. It is not a black hole, which refers to the trap around it. It is a star. But it is a star made of the smallest units of existence. So physicists have given it a name that honors the father of quantum mechanics. We call this object a Planck star. Now, I want you to visualize it. I want you to see it in your mind. This is the most mind-blowing part of the entire theory. When we say star, you imagine a giant ball of fire like our sun. You imagine something huge, but the Planck star is not huge. The Planck star is the master of disguise. How big is it? Let's take a normal black hole. Let's say a star 30 times heavier than our sun collapsed. It creates a black hole with an event horizon that is maybe 50 miles wide. That is the black sphere you see in the movies. That is the shadow, but that is just the curtain. The Planck star is hiding inside that 50-mile sphere. Is the Planck star the size of a city? No. Is it the size of a house? No. Is it the size of a baseball? No. The Planck star, which contains the crushed mass of 30 suns, is roughly the size of a single atom. Let that sink in. Do not just listen to the words. Feel the absurdity of that statement. A single atom. A speck of dust so small you need a microscope to see it. Now, imagine walking up to that tiny speck. You try to pick it up, but you can't, because that tiny speck weighs as much as 30 million Earths. It weighs as much as a solar system. If you placed this atom on the surface of the Earth, it wouldn't just sit there. It would fall right through the planet like a cannonball falling through fog. It would eat the Earth from the inside out just by its gravitational presence. This is the scale of the mystery. This is why the singularity was such a convincing lie. The object is so small that it is easy to mistake it for nothing. It is easy to round it down to zero. But there is a universe of difference between zero and an atom. Zero is nothing. An atom is something. Because it is something, it has a surface. It has a volume. It occupies space. And most importantly, because it is something, it can act. A singularity is a dead end. A Planck star is a living object. So, what does it look like? If you could somehow survive the gravity, strip away the darkness of the event horizon, and shine a flashlight on the center, what would you see? You wouldn't see a rock. You wouldn't see a ball of iron. You would see a glitch in reality. Because the density is so high, the Planck star interacts with light and time in ways we can barely describe. It is likely a seething, vibrating ball of quantum foam. It is glowing, but not with light as we know it. It glows with high-energy gamma radiation. It is a knot in the fabric of space. It is like a stress ball that has been squeezed by a giant until it is hard as stone. This little atomic-sized star is holding on to all the information of the things that fell into it. Remember the books, the planets, the light that got sucked in? They didn't vanish. They are plastered onto this Planck star. They are encoded in the quantum vibrations of this tiny dense jewel. The black hole is not a garbage disposal. It is a safe deposit box. And the Planck star is the diamond sitting inside the box. But there is a tension here. A tension that drives the rest of our story. Imagine you're holding a spring. You squeeze it between your thumb and forefinger. You squeeze it until the coils are touching. You squeeze it until your fingers are shaking with the effort. Is the spring stable? No. The spring is desperate. The spring is angry. The spring wants to do one thing and one thing only. It wants to explode. The Planck star is not a tombstone. It is a loaded gun. It is a bomb that has been armed and is waiting for the timer to hit zero. The quantum pressure we talked about earlier, the force that stopped the collapse, is not just holding the weight of the star. It is pushing back. It is fighting for its life. The gravity is pushing in, trying to crush it to zero. The Planck star is pushing out, trying to expand back into a normal star. Right now, in the center of the darkness, there is a stalemate. The forces are balanced. The space pixels are holding the line. But they won't hold it forever. We have visualized the object. We have named it. We have realized that the terrifying black hole has a tiny, heavy, beating heart. But this brings us to the most obvious question. The question that any child would ask. If this star is actually a bouncing spring, and if it wants to explode, why hasn't it? Why do black holes look like they last forever? Why don't they pop like balloons the moment they form? If the bounce happens immediately after the crash, we should see fireworks. We should see the star collapse and immediately expand. it should be a quick process. Crash, bounce. But when we look at the sky, we see quiet, silent darkness. We see black holes that have been sitting there for billions of years. Is the theory wrong? Did we miss something? No. We didn't miss something. We forgot something. We forgot about Einstein. We forgot that when you are near something this heavy, the universe plays a trick on you. A trick that freezes reality itself. The Planck star is bouncing. It is exploding right now, but we can't see it. We are about to discover the time trap. We have built the star. Now we have to understand why it is frozen in time. The slow-motion explosion is about to begin. And trust me, the explanation for why it takes so long is the most beautiful part of the puzzle. The Planck star is real. It is small. It is heavy. And it is waiting for us to catch up. Chapter 5. The Bounce. We have arrived at the moment that changes everything. Up until now, we have been building a picture of a solid object hiding in the dark. We found out the singularity is a lie. We discovered the pixels of space. We watched the star collapse and hit the floor of the universe to form the Planck star. But even now, if I asked you to picture a black hole, you would still imagine something static. You are likely picturing a dark ball sitting in space, heavy and silent, like a tombstone made of gravity. You are imagining that the collapse happens, the star hits the bottom, and then it just stays there. We think of black holes as things that last forever. We think of them as the final resting place of matter. But I am here to tell you that this image is not just slightly wrong. It is the exact opposite of the truth. Prepare yourself for the twist. Prepare to have your entire concept of a black hole flipped upside down. The Planck star is not sitting still. It is not resting. It is not a statue. The object inside the black hole is actually moving, and it is moving with a violence that defies comprehension. The reason you are confused is that you are thinking of the floor of the universe like a concrete pavement. You think that when the star hits the space pixels, it goes splat and stops. But the fabric of reality is not concrete. It is elastic. The quantum fabric of space is more like a trampoline. It is more like a bed of high-tension springs. When you drop a bowling ball onto a trampoline, what happens? Does it hit the bottom and stay there? No. It stretches the fabric down, stores all that energy, and then immediately, without hesitation, it throws the ball back up. This is the secret of the Planck star. It is not a stopped star. It is a bouncing star. To understand this, we have to look at the physics of compression. Think about a rubber ball. If you hold it in your hand and squeeze it, you are putting energy into it. If you throw it against a wall, it squashes flat for a millisecond. In that millisecond, the ball is under tremendous stress. Every molecule in the rubber is screaming. It wants to return to its original shape. The harder you throw it, the harder it bounces back. This is a fundamental law of nature. Action and reaction. Compression and rebound. Now take that rubber ball and replace it with a star that weighs 30 million times the mass of the Earth. Take the wall and replace it with the unbreakable grid of quantum geometry. Gravity throws the star against the quantum wall at the speed of light. The star crushes down. The space atoms compress. The pressure rises to numbers that we don't even have names for. The quantum foam is squeezed until it screams. And what happens next? Nature does what nature always does. It rejects the squeeze. It pushes back. The Planck star doesn't just sit there being heavy. It immediately reverses its direction. The collapse ends and the explosion begins. This is the part that breaks people's brains. We are taught that a black hole is a collapse. We are taught it is a one-way street. Things go in, nothing comes out. But loop quantum gravity suggests that the collapse is only half of the story. A black hole is actually a star that is collapsing and then immediately exploding outward. The collapse and the explosion are not two separate events. They are one single continuous motion. Think of a heart beating. Thump, thump. The contraction and the expansion are part of the same cycle. You cannot have one without the other. Think of a diver jumping off a high board. They hit the water, go down, slow to a stop, and float back up. It is one fluid journey. The life of a star is exactly the same. The star lives, burns fuel. The star dies, collapses. The star hits the quantum floor, Planck star. The star bounces, white hole. So the object in the dark is not a hole at all. A hole implies an empty space that things fall into and get lost. This is a trap. The correct way to think of a black hole is as a rebound. It is a star that is currently in the process of turning itself inside out. It is a star that is trying to blow up. This completely rewrites the villain narrative we talked about earlier. Gravity isn't the winner. Gravity is just the force that loads the spring. Gravity pulls the bowstring back, but quantum mechanics is the fingers that let the arrow fly. The black hole is simply the moment the bow is fully drawn, tension trembling in the air right before the release. But hold on, stop, take a breath. Because if you are paying attention, you should be spotting a massive, glaring contradiction. You should be angry with me right now. You should be looking at the screen and shouting, "Wait a minute!" Let's look at the logic. Point A, I just told you the star hits the floor and bounces immediately. A rubber ball doesn't wait 10 years to bounce. It bounces instantly. The reaction is fast. Point B, we look at the sky with our telescopes. We see black holes. We have been watching them for decades. We know they have been there for millions, sometimes billions of years. They are not exploding. They're just sitting there, dark and silent. How can both of these things be true? How can the star be bouncing instantly, and yet the black hole lasts for billions of years? If the Planck star is a bomb that has already detonated, why are we still seeing the fuse? Why haven't we seen the explosion? Why does the universe look so quiet? This is the retention hook. This is the mystery that will haunt you. If I throw a ball at the ground, it bounces in less than a second. If a star throws itself at the quantum ground, it should bounce in a fraction of a second. So where is the bounce? Why do black holes look like eternal prisons if they are actually fleeting bounces? The answer lies in the greatest illusion of the universe. The answer lies in the fact that your eyes are lying to you. You see, you are watching the movie of the universe from the safety of Earth. You are far away from the gravity. You are sitting in the cheap seats of the cosmos. But down there, down in the pit, the rules of the game are different. The star is bouncing. It is bouncing fast. It is bouncing instantly. But we are not seeing it fast. We are witnessing a slow motion disaster. Imagine you recorded a video of a grenade exploding. It takes a millisecond. Bang. Done. Now imagine you play that video back, but you slow it down. You slow it down so much that 1 second of the video takes 1 billion years to watch. What would you see on the screen? You would see the fire starting to expand, but it would look frozen. It would look like a static ball of fire. It wouldn't look like an explosion anymore. It would look like an object. This is the twist that connects the theory to reality. The black hole is not an object. It is an event. It is a split-second bounce that has been stretched out over eons. We are not looking at a thing. We are looking at a happening that is taking forever to happen. The tension of the Planck star is the tension of a held breath. It explains why black holes exist. They are simply stars that are taking a very, very long time to die. But this creates a terrifying thought. If the video is playing in slow motion, what happens when the video catches up? What happens when the slow motion stops? If the black hole is actually a bouncing star, that means eventually the bounce has to finish. Eventually the ball has to come back up. The standard theory says black holes evaporate slowly and vanish. The Planck star theory says something much more violent. It says that one day the black hole will stop being black. It says that one day the event horizon trap will snap open, and everything that fell in, the light, the matter, the secrets, will be vomited back out into the universe in a blinding flash of glory. We used to ask, what is at the bottom of the black hole? Now we know the answer: a bouncing star. But the new question is even more important. The new question is, when will we see the splash? The paradox of the instant bounce versus the eternal black hole is not a mistake in the math. It is a clue. It is a clue that leads us to the strange warping power of gravity itself. To understand why the bounce is hidden from us, we have to understand the time trap. We have to understand that now for you is not the same as now for the star. You are living in the fast lane. The Planck star is living in the pause button. The bounce is real. The explosion is happening. But gravity has trapped the explosion in a cage of frozen time. Next, we are going to walk into that cage. We are going to explain exactly how gravity steals time. And we are going to realize that while we live, age, and die, the star inside the hole hasn't even finished blinking. The mystery box is open. The contents are moving. The star is alive. But to see it move, we have to learn how to watch the universe with new eyes. Are you ready to learn why a second can last 1 billion years? Because that is the only thing keeping the Planck star from blowing us all away. Chapter 6. The Time Trap. We are standing at the edge of the greatest magic trick in the universe. In the last chapter, I dropped a bomb on your reality. I told you that the black hole, that dark, silent, eternal prison we see in the sky, is actually a lie. I told you that deep inside, the star is not dead. It is not sitting still. It is actually bouncing. It has hit the floor of the universe and is exploding outward right now. But this creates a massive, headache-inducing problem. If the star is exploding, why can't we see the explosion? If the bounce happens instantly, like a rubber ball hitting the ground, why do black holes look like they last for billions of years? Why is the universe full of these dark traps instead of bright fireworks? The answer is not in the star. The answer is in the watcher. The answer lies in the single most confusing, terrifying and beautiful concept in all of physics. To understand the Planck star, we have to understand the time trap. You have probably heard that time is relative. You have heard it in school, or maybe you saw it in a movie. But most people don't really feel what that means. We think of time as a steady river. We think 1 second for me is 1 second for you, and 1 second for a star in a distant galaxy. We think time is the background noise of the universe that never changes. But Einstein taught us that this is wrong. Time is not a river. Time is a map. And just like a map has hills and valleys, time has fast spots and slow spots. And the thing that creates these hills and valleys is gravity. Think back to the movie Interstellar. Remember the water planet? The heroes land on a planet that is orbiting close to a massive black hole. They stay there for a few hours, but when they get back to their ship, their friend has aged by years. Why? Because they were deep in a gravity well. The gravity of the black hole was pulling on time itself, stretching it out like a piece of chewing gum. On that planet, 1 hour was equal to 7 years back on Earth. It sounds like fiction, but it is absolute, proven fact. Your GPS satellites have to adjust their clocks every single day because time moves slightly faster in space than it does here on Earth. Gravity slows down the clock. Now, take that concept and crank it up to maximum. The planet in Interstellar was just near a black hole. It was on the edge. But the Planck star we are talking about, it is not near the edge. It is in the center. It is in the deepest, darkest, heaviest pit of gravity that nature can create. The gravity down there isn't just strong, it is monstrous. It is so intense that it doesn't just stretch time, it practically strangles it. This brings us to the 2 clocks analogy. This is the key to unlocking the mystery. Imagine we have 2 watches. Identical watches, synchronized perfectly. You keep one watch here on Earth, safe and far away from the black hole. We will call this the outside clock. I take the other watch and I jump onto the surface of the dying star, just as it begins to collapse. We will call this the inside clock. I ride the star down. I fall into the darkness. I am holding my watch. To me, the inside watcher, the collapse is terrifyingly fast. I fall. I see the star shrink. I feel the crushing weight. I hit the space pixels, the floor. I bounce. According to my watch, this entire process, the collapse, the hit, and the start of the bounce, takes a fraction of a second. It happens in a heartbeat. Thump, thump. I hit the ground and I bounce back up. To me, the black hole is a momentary event. It is a car crash. It is over before I can even scream. But what do you see? You are looking at your outside clock. You are watching me through a powerful telescope. As I get closer to the center, the gravity starts to grab the light I'm sending you. It grabs the information of my fall, and it grabs time itself. You see me falling. But as I get closer to the darkness, I start to slow down. My movements become sluggish. My scream deepens into a low, frozen drone. On my watch, 1 second passes. On your watch, 1,000 years pass. I move another inch. On your watch, 1,000,000 years pass. By the time I hit the floor and start to bounce, billions of years have passed in your universe. Civilizations have risen and fallen. Stars have burned out. The universe has aged. To you, I am frozen. To you, I am stuck in a state of eternal falling. You never see me hit the bottom. You never see me bounce. You just see me fading into the dark, suspended in a timeless amber. This is the illusion. The paradox of the instant bounce versus the eternal black hole is solved. Both things are true. For the star, the life of a black hole is a split-second explosion. For us, the watchers, that split second is stretched out over the entire lifetime of the universe. A black hole is not a place where time stops. It is a place where time is hoarded. Think of a video player. The reality of the star is the movie file. The movie is an action scene. It is an explosion. It is fast, violent, and loud. But gravity is the hand on the remote control. As the star collapses, gravity presses the slow-motion button, and it presses it so hard that the frame rate drops to 0. We are watching a high-speed explosion, but we are watching it at 1 frame per trillion years. We look at the screen and say, "Hey, that's a static picture. That's a black hole. It's not moving." But it is moving. It is just moving so slowly relative to us that it looks like a hole. This completely changes the personality of the object in the sky. We used to think of black holes as monsters that eat everything. We thought they were greedy. But the Planck star theory tells us they are not greedy monsters. They are time capsules. They are events that have been sequestered from our timeline. They are bubbles of fast time trapped inside a shell of slow time. This is why the black hole looks dark. Light tries to escape the bounce. The energy of the explosion is trying to rush out. But the gravity is so steep that the light has to climb a vertical wall of time to get to us. It loses all its energy climbing out of that deep gravity well. It gets red-shifted into invisibility. The light is there. The image of the exploding star is there. But it is trickling out so slowly that our eyes perceive it as a shadow. We are witnessing a crash in pause mode. Imagine 2 cars smashing into each other, metal crunching, glass flying. Now freeze that moment. Walk around the frozen wreckage. It looks like a sculpture. It looks solid. You can touch it. You can study it. It looks like a permanent object. But if you unpause the world, that object would instantly fly apart in a violent release of energy. That is exactly what a black hole is. It is a star crash that gravity has paused for our viewing pleasure. This realization should give you chills. When you look at that famous photo of the black hole, that glowing orange donut with the dark center, you are not looking at a hole. You are looking at a delayed explosion. The star has already died. It has already hit the floor. It has already started to push back. The bounce has already happened. But the news hasn't reached us yet. The update notification is stuck in the spam filter of gravity. This resolves the tension we felt in the last chapter. Why doesn't it explode? It is exploding. Why does it take so long? Because gravity is the ultimate brake pedal. But here is the thought that should keep you up at night. The thought that leads us to the next chapter. If a black hole is just a slow-motion explosion, what happens when the movie finishes? You cannot pause a movie forever. Eventually, the information has to get out. Eventually, the outside clock catches up to the inside clock. Eventually, the gravity weakens just enough, or the universe waits just long enough for the slow motion to speed up again. When that happens, the illusion will break. The pause button will release. The slow motion will turn into fast forward. And the thing that we thought was a dark, silent pit will reveal its true face. It will stop sucking things in, and it will start spitting them out. We are about to transition from the darkness to the light. We have seen the black hole. Now we must meet its twin. We must meet the object that appears when the clock finally strikes midnight. We must meet the white hole. The time trap is strong, but it is not infinite. Nothing lasts forever, not even a black hole. The bounce is coming, and when it arrives, it will be the brightest thing the universe has ever seen. Are you ready to see what happens when the play button is finally pressed? Chapter 7. The White Hole Connection. We have been holding our breath for billions of years. In our journey so far, we have frozen time. We have watched a massive star collapse, hit the hard, pixelated floor of the universe and begin to bounce. But because of the crushing weight of gravity, that bounce has been trapped in a cage of slow motion. We left the story at a cliffhanger. The star is screaming to explode, but the universe has hit the pause button. But now we have to ask the question that unlocks the wildest concept in science fiction. What happens when the movie starts playing again? What happens when the time trap finally fails? If the black hole is the pause, then what does the play button look like? The answer leads us to a mythical object. An object that physicists have whispered about for decades, usually assuming it was nothing more than a mathematical ghost. We are about to meet the twin brother of the black hole. We are about to meet the white hole. If you are a fan of science fiction, you know what a white hole is supposed to be. In the movies, they are magical portals. They are cosmic geysers that spew out energy and matter from another dimension. They are the good guys to the black hole's bad guy. But in the real world of standard physics, white holes were always considered impossible. They were dismissed as a fantasy. Einstein's equations allowed them to exist on paper, but nobody believed they could exist in reality. Why? Because a white hole is defined as the reverse of a black hole. A black hole is a place where everything goes in and nothing comes out. A white hole is a place where everything comes out and nothing can go in. It sounds ridiculous. It sounds like a video played backward. It violates our common sense. But remember our hero? Remember loop quantum gravity? This theory doesn't care about our common sense. It cares about the space pixels and the bouncing star. And according to this theory, the white hole is not a fantasy. It is not a magic portal to another dimension. It is something much more real and much more shocking. The white hole is the destiny of every black hole. Let's go back to the slow-motion explosion. We know the star is trying to expand. It is pushing outward against the crushing grip of gravity. For eons, the black hole sits there, dark and silent, evaporating very slowly due to something called Hawking radiation. As it evaporates, it loses mass. As it loses mass, its gravity gets a little bit weaker. The grip loosens. The time trap becomes a little less tight. The cage begins to rust. Eventually, a moment arrives that changes cosmic history. The black hole shrinks down to a specific, critical size. It becomes small enough that the rules of quantum mechanics take over completely. The quantum pressure of the bouncing star inside becomes stronger than the gravity holding it in. The balance tips. The stalemate ends. In a fraction of a second, the event horizon, the invisible line that trapped the light, vanishes. The trap snaps open. The pause button releases, and the star, which has been trying to bounce for billions of years, finally gets its wish. Boom! The object suddenly stops being black. It stops sucking things in. It flips its identity entirely. It becomes a brilliant, blinding beacon of light. It spits out everything it ever swallowed. The collapse reverses into an expansion. This expanding object is the white hole. This is the revelation that maximizes viewer retention. A black hole and a white hole are not two different objects. They are the same object, seen at different times in its life. Think of a butterfly. You have a caterpillar, the collapsing star. It wraps itself in a chrysalis, the black hole. It sits there dormant, hidden and mysterious for a long time. But eventually the chrysalis breaks open, and a butterfly, the white hole, emerges. You wouldn't say the caterpillar and the butterfly are enemies. You wouldn't say they are unrelated. They are just stages of a metamorphosis. The universe is doing the same thing. The black hole is the inhale. The white hole is the exhale. This solves one of the biggest headaches in physics. Scientists used to think white holes were impossible because they couldn't figure out how to make one. You can make a black hole easily. Just crush a star. But how do you make an object that only spits things out? It seemed to require running the universe backward. But the Planck star theory gives us the recipe. You don't need magic, you just need patience. You just have to wait for a black hole to die. When a black hole dies, it doesn't vanish, it transforms. Imagine you're holding a beach ball underwater. You are the gravity. The ball is the star. As long as you're strong enough, you can hold that ball down in the dark depths. That is the black hole phase. But your arms get tired. Your strength fades. Evaporation. Eventually, you cannot hold it anymore. Your grip slips. What happens to the ball? Does it stay down there? No. It shoots up toward the surface with incredible speed. It breaches the water and flies into the air. That moment, the breach and the upward flight, is the white hole phase. So, what would this look like if you were watching it? For billions of years, you would see a dark spot, a shadow. But then, in a flash of gamma rays and high-energy particles, the shadow would tear apart. The Planck star, no longer hidden by the dark horizon, would expand explosively. It is the bounce we promised in Chapter 5, finally becoming visible to the outside world. This connection creates a beautiful symmetry in the universe. Nature loves symmetry. Gravity pulls in, pressure pushes out, stars collapse, stars explode, black holes swallow, white holes eject. It turns the cosmos into a breathing organism. It means the story of a star doesn't end in darkness. It ends in light. The villain of the story, the bottomless pit, was just a misunderstood hero waiting for his time to shine. But there is a twist here that involves you. Imagine you were brave enough, or foolish enough, to jump into the black hole back in Chapter 6. Remember, you fell in and time froze for you. You hit the bounce. To you, it happened instantly. So, where do you end up? If you survive the crushing forces, which granted is a big if, you don't die in the dark. You ride the bounce, you ride the expansion, you get shot out of the white hole. But when do you come out? You fell in today. But because of the time trap, the black hole doesn't turn into a white hole for billions of years. So, you fall in on a Tuesday in 2024. You hit the bounce, and you are spit out of the white hole in the year 30 billion. You have just travelled to the deep, distant future. The black hole-white hole connection is not just a trash compactor and a recycling bin. It is a one-way time machine. It transports matter from the present era of the universe to the dying days of the cosmos. This is why the concept is so viral. It takes the terrifying finality of death and replaces it with a portal to the future. It tells us that nothing is truly trapped forever. Even the ultimate prison has a key. That key is the white hole. However, there is a lingering question that makes this even more intriguing. If every black hole eventually becomes a white hole, why don't we see them everywhere? The sky should be filled with popping white flashes. It should look like paparazzi cameras going off in deep space. The answer lies in the lifespan. Massive black holes, like the one in the center of our galaxy, take an unimaginably long time to evaporate and reach the white hole transition. They will not turn into white holes until long after the stars have burned out. The universe is too young to see the big ones pop. We are living in the black hole era. The white hole era is yet to come. But what about the little ones? Remember the primordial black holes? The tiny ones the size of protons? They don't have to wait billions of years. Their timers are short. They could be popping right now. This means that white holes might not just be a theory for the distant future. They might be happening in our backyard. They might be the mysterious signals our telescopes are picking up today. The white hole connection bridges the gap between the dark gravity of Einstein and the bright explosions of quantum mechanics. It turns the impossible error of the singularity into a doorway. It tells us that the universe is a cycle. What goes down must come up. What falls in must come out. The slow-motion explosion eventually finishes its scene. But there is one final piece of the puzzle that we need to address to satisfy the smartest viewers. We talked about information. We talked about the books and the secrets falling into the hole. When the white hole spits everything out, does it spit out the books? Does it spit out the secrets intact? Or does it just spit out a scrambled mess of energy? This is the information paradox, and the white hole is the solution to the biggest argument in the history of physics. Stephen Hawking bet against it. He thought the information was lost. The Planck star says he was wrong. The white hole is not just spitting out energy, it is spitting out memory. It is returning the lost history of the universe. In the next chapter, we are going to look at exactly how the Planck star saves the data. We are going to look at the hard drive of the cosmos. We have seen the explosion. Now we need to see the message hidden inside the blast. The white hole is open. Let's see what comes out. Chapter 8. Saving the information. We have reached the part of the story that keeps the smartest people on Earth awake at night. We have talked about crushing stars, bouncing floors, and time traps. We have built a picture of a universe that is violent, strange, and beautiful. But there has been a dark cloud hanging over this entire series. A cloud that threatens to ruin everything we have discovered so far. You see, for the last 50 years, physics has been fighting a civil war. It is a war over a single question. It is not a question about gravity. It is not a question about light. It is a question about memory. The question is, when something falls into a black hole, is it gone forever? Does the universe forget it existed? For decades, the answer appeared to be yes, and that answer was a catastrophe. It was known as the information paradox. But today, the Planck star is going to step in and save us from this nightmare. The Planck star is going to prove that the universe never forgets. To understand why this is such a big deal, you have to understand the most sacred rule of quantum mechanics. It is a rule called unitarity. It is a fancy word, but the concept is simple. Information can never be destroyed. Imagine you have a precious book, a first edition, one of a kind. If you take that book and throw it into a fireplace, it burns. It turns into ash and smoke. To you and me, the book is gone. The information inside it is lost. But to a physicist, the information is still there. If you could capture every single particle of ash, every wisp of smoke, and every photon of light from the fire, and if you had a supercomputer powerful enough, you could, in theory, reverse the physics. You could rewind the motion of the atoms and reconstruct the book perfectly. The ink, the paper, the words, it is all still there, just scrambled. This is the bedrock of science. It means that the past determines the future. It means that if you know the state of the universe now, you can reconstruct the past. The universe is a perfect record keeper. It does not lose files. But then along came the black hole. According to the old theories, the ones based on the singularity, black holes are the ultimate cosmic shredders. If you throw that book into a black hole, it crosses the event horizon. It gets sucked into the dark. And then, according to Stephen Hawking's early calculations, the black hole slowly evaporates. It breathes out heat called Hawking radiation. It shrinks and shrinks over billions of years until, poof, it vanishes. It disappears completely. And here is the horror. The radiation that comes out is random. It contains no data. It contains no secrets. It is just heat. So, look at the timeline. The book goes in, the black hole eats it, the black hole disappears, the book is gone. This is not like the fire. There is no ash to analyze. There is no smoke to reverse. The information has simply been deleted. It has been erased from the hard drive of reality. This realization sent a wave of panic through the scientific community. If black holes destroy information, then quantum mechanics is wrong. If quantum mechanics is wrong, then our understanding of atoms, chemistry, and existence itself is built on a lie. It was a crisis. Physicists were screaming at each other at conferences. It was a battle between the universe makes sense and the universe is broken. The singularity was the villain because a singularity has zero size. It has no surface area. It has no capacity to store data. If you squeeze 1 trillion books into a zero-dimensional point, you can't read them anymore. You can't even store them. They just vanish. But now, enter the hero. Enter the Planck star. Remember what we learned in Chapter 3? The universe is pixelated. Space has grains. The center of a black hole is not a zero point. It is a solid object with a surface. It is a ball of space atoms. And because it is a solid object, it has a special property that saves the day. It can act as a hard drive. The solution to the information paradox is found in the structure of the Planck star itself. When matter falls into the black hole, it doesn't just disappear into a void. It hits the Planck star. It crashes into those tiny quantum loops. And when it crashes, it leaves an imprint. Imagine the Planck star is like a giant ball of wet clay. When you throw a rock at it, the rock sinks in, but it leaves a dent. It changes the shape of the clay. The information of the rock, its mass, its speed, its angle, is encoded into the shape of the clay. Now, scale that up to the quantum level. The space pixels of the Planck star rearrange themselves, they vibrate, they form a pattern. The book that fell in is not destroyed. Its atoms are crushed, yes. Its pages are torn apart, yes. But the quantum information, the fundamental description of what that book was, is etched onto the surface and the interior of the Planck star. This changes the black hole from a shredder into a vault. The black hole is not destroying the universe's memory. It is simply archiving it. It is taking the things that fall in, compressing them into the tightest possible file format, Planck density, and storing them on the most durable storage device in existence. The singularity couldn't do this because it had no pixels to write data onto. But the Planck star has trillions of pixels. It has the capacity to hold the data. But storing the data is only half the battle. If I lock your files in a safe and then throw the safe into the ocean, the information is technically saved. but it is useless if you can never get it back. For the universe to preserve its laws, the information has to be returned. It has to come back out. This is where the white hole connection from the last chapter becomes the savior of physics. Remember the slow-motion explosion? Remember that the black hole eventually stops holding its breath and bounces? When that bounce happens, the event horizon disappears. The trap opens. The Planck star expands explosively outward. And what comes out with it? Everything. All the light, all the matter, and most importantly, all the information. The Planck star, which has been storing the data of everything it swallowed for billions of years, spits it all back out into the universe. The book comes back. Now, it doesn't come back as a readable paper book. It comes back as a scrambled stream of particles and radiation. But, and this is the crucial part, the correlations are there. The pattern is there. If you had that supercomputer we talked about earlier, you could look at the explosion of the white hole and reconstruct the book. The file was not deleted. It was just zipped, password protected, and hidden in a folder called Black Hole for a few eons. And now the folder has been unzipped. This resolution is profound. It means that physics is safe. It means that Stephen Hawking's terrifying prediction of information loss was based on the impossible error of the singularity. Once you replace the error with the Planck star, the paradox evaporates. The universe is not senile. It does not have Alzheimer's. It remembers every single atom that was ever created. Think about the implications of this. It means that deep inside the monstrous gravity of the black hole, there is a record of the past. If our Earth were to be swallowed by a black hole tomorrow, we would die. Our cities would be crushed. But the description of us, the quantum blueprint of who we were, what we built, and what we knew, would be preserved on the surface of the Planck star. We would become part of the star's memory, and billions of years from now, in the glorious flash of a white hole, that memory would be broadcast back out to the stars. The Planck star essentially acts as a cosmic backup system. This theory satisfies the intellectual viewer because it bridges the gap between general relativity, gravity, and quantum mechanics, data. General relativity says, things fall in. Quantum mechanics says, data must survive. Loop quantum gravity says, things fall in, get stored on the Planck star, and survive to be released later. Everyone wins. The laws of nature are consistent. There are no holes in the logic anymore, but it also adds a layer of beauty to the violence. We usually see black holes as engines of destruction. We see them as death. But this theory suggests they are actually engines of rebirth. They take the old, dead matter of the universe, scrub it down to its quantum foundations, store it, and then recycle it back into the cosmos to build new stars, new planets, and maybe new life. The information is not just saved, it is recirculated. This changes how we look at the entire history of the universe. It is not a story of things slowly fading away. It is a story of constant recycling. The information paradox was a fear that the story had missing pages. The Planck star assures us that the book of the universe is complete. No pages have been torn out. The story is whole. So, the next time you hear a scientist talking about the crisis in physics or the mystery of information loss, you can smile. You know the secret. You know that the crisis comes from believing in the singularity. You know that if you look deep enough, past the event horizon, past the darkness, down to the pixelated grid of reality, there is a hard drive spinning. There is a Planck star holding onto the data, waiting for the right moment to hit upload. The data is safe. The past is secure. And the future is going to be incredibly bright when all those white holes finally start to pop. We have solved the paradox. We have saved the science. But now we have one final hurdle. We have a beautiful theory. We have a perfect story. But science isn't about stories. It is about proof. Is this all just a fantasy? Or is there actually evidence in the sky right now that proves Planck stars are real? Can we see them? In the next chapter, we are going to turn our telescopes to the dark. We are going to look for the fingerprints of the Planck star. And we might just find that the evidence has been staring us in the face this whole time. The theory is sound. Now, let's hunt for the reality. Chapter 9. The evidence. Are they real? We have spent the last few minutes building a castle in the sky. We have constructed a magnificent theory where black holes are not murderers, but mothers. We have imagined a universe where stars bounce, where information is saved, and where the timeline of the cosmos loops in a beautiful circle. It is a perfect story. It solves the paradoxes. It fixes the math. It makes us feel good about the nature of reality. But there is a brutal truth that we have to face right now. In the world of science, a beautiful story is worthless if it is not true. You can write the most elegant equation in history, but if nature doesn't agree with you, you are wrong. Science is not about what we want to be true. It is about what we can prove. So we have to ask the hard question. We have to be the skeptic. Is the Planck star real? Or is it just a fantasy invented by physicists who are afraid of the dark? To answer this, we have to look at the biggest obstacle standing in our way. That obstacle is time. Remember the time trap from Chapter 6. We learned that because gravity is so strong, the bounce of a normal black hole is stretched out over billions and billions of years. If a star collapses today, it won't explode as a white hole until the universe is old, cold, and dead. This is a massive problem for us. We human beings do not live for billions of years. We cannot set up a camera, point it at a black hole, and wait for the show to start. If the only Planck stars in existence are the ones inside the massive black holes we see in the night sky, then we will never see one. We will never get our proof. We will die wondering. But what if there were other black holes? What if there were black holes that were not made by dying stars? What if there were black holes that were born with a short fuse? This is where the detective story gets really interesting. We have to travel back in time, all the way back. We have to go to the Big Bang. We usually think of the Big Bang as a smooth explosion that created the universe. But physicists believe the early universe was actually a mess. It was chaotic, it was violent, it was lumpy. In the first fraction of a second, the density of the universe was uneven. Some spots were thicker than others, and in those superdense spots, matter was squeezed so hard by the violence of the explosion that it collapsed into black holes instantly. These are not stellar black holes formed by dead stars. These are primordial black holes. They are the ancient relics of creation. Here is the key difference. Primordial black holes can be any size. A star has to be huge to collapse, but a primordial black hole could be the size of a mountain. It could be the size of a bowling ball. It could be the size of a grain of sand. It could be the size of a single proton. Why does size matter? Because in the strange world of loop quantum gravity, size equals time. The bigger the black hole, the deeper the gravity well, and the longer the slow motion effect lasts. But a tiny black hole has weak gravity. It doesn't warp time as much. The time trap is weaker. The slow motion isn't as slow. This means a tiny black hole doesn't take trillions of years to bounce. It might only take 1 billion years, or 1 million years, or 1,000 years. Now, do the math. The universe is roughly 13.8 billion years old. If the Big Bang created trillions of tiny black holes of all different sizes, then statistically there should be a specific size of black hole whose timer is set to exactly 13.8 billion years. There should be a specific size of primordial black hole that has been holding its breath since the dawn of time, waiting through the formation of galaxies, waiting through the dinosaur age, waiting through the rise of humans, and is ready to explode right now. This is the smoking gun we are looking for. We are not looking for the giant monsters in the center of the galaxy. We are looking for the tiny invisible mines floating in deep space. We are looking for black holes that are roughly the size of a proton, but weigh as much as a mountain range. These objects have reached the end of their life cycle. The time trap has finally expired. The slow motion has caught up to the present day. So if these things are real, and if they are exploding today, what would we see? We wouldn't see a giant fireball. These things are tiny. When the Planck star inside them finally expands and turns into a white hole, it releases all its energy in a pulse that matches its size. Because the hole is the size of a subatomic particle, the light it emits is not visible light. It is not radio waves. It is the shortest, most energetic wavelength in the universe. It is a flash of gamma rays. A gamma ray is the scream of a nucleus. It is high-energy light, and the theory predicts that when a primordial Planck star explodes, it should produce a very specific signature in the sky. It shouldn't look like a normal supernova. It shouldn't look like a quasar. It should look like a sharp, distinct pop of high-energy light. It would be a signal that appears out of nowhere, flashes brilliantly in the gamma spectrum, and then vanishes. And here is the part that should give you goosebumps. We have built machines to look for exactly this. We have telescopes like the Fermi Gamma Ray Space Telescope orbiting the Earth right now. Its entire job is to scan the heavens for invisible flashes of gamma radiation. And over the years, astronomers have seen things. They have seen fast radio bursts. They have seen gamma ray bursts. Many of these are explained by other things, like colliding neutron stars. But there are some signals, some strange fleeting flashes in the dark, that we still cannot explain. There is a distinct possibility that we have already seen a Planck star. It is possible that in the databanks of NASA, hidden in a spreadsheet of unidentified anomalies, sits the proof that the universe bounces. Scientists are currently combing through this data. They are refining the models. They are calculating exactly what the color of the explosion should be. They are looking for a specific frequency that would prove without a doubt that the signal came from a bouncing black hole and not a dying star. If they find it, it changes everything. Think about the stakes. If we confirm the existence of a single exploding primordial black hole, we prove that loop quantum gravity is correct. We prove that space is made of pixels. We prove that the singularity is an error. We prove that the universe recycles information. We prove that the impossible error was just a lack of imagination. But there is another possibility, a scarier one. What if we look and look and look and we find nothing? What if the sky is silent? If we don't find these explosions, it might mean that primordial black holes don't exist. Or it might mean that the time trap is even stronger than we thought. It might mean that the bounce takes so long that even the tiniest black holes haven't finished yet. It would mean we are trapped in the black hole era forever. And the white hole era is a dream that will only happen after all life in the universe is extinct. This is why the search is so intense. We are racing against our own ignorance. We are looking for a needle in a haystack, but the needle is the size of a proton, and the haystack is the entire observable universe. However, the evidence is mounting, the math is solidifying, and just recently some astronomers have suggested that the mysterious dark matter that holds galaxies together might actually be swarms of these tiny, unexploded Planck stars. They might be everywhere. We might be swimming in a sea of tiny frozen explosions, unaware of the power hidden in the dark. The transition from theory to reality is messy. It is hard work. It requires staring at static on a screen for years. But the payoff is the ultimate answer to the ultimate question. Is the universe a dead-end street, or is it a circle? The evidence lies in the pop. We are listening, we are watching, and every time a gamma-ray detector pings, a physicist's heart skips a beat, because that ping might be the dying breath of the Big Bang, telling us that the universe is alive. The hunt is on. The detectives are working, and while they search for the proof, we can step back and look at the big picture. Because if this theory is true, if black holes bounce, then it leads to one final grand conclusion. A conclusion that goes beyond stars and atoms. A conclusion that touches the origin of US. If a star can bounce, can a universe bounce? We have reached the end of the evidence. Now we must face the grand finale. We are about to zoom out. We are about to realize that the Planck star is just a miniature version of something much, much bigger. Are you ready to see the breathing universe? Chapter 10. The Breathing Universe. We have reached the end of our journey. We started this story by looking at a single dying star. We watched it collapse under the crushing weight of gravity. We saw it hit the hidden pixels of the universe. We watched it turn into a Planck star. And we realized that the dark silence of a black hole is actually a slow-motion explosion waiting to burst into a dazzling white hole. It has been a wild ride through the laws of physics, but if you thought the story ended with black holes, you were wrong. Because physics is not just about the parts, it is about the whole. If the laws of loop quantum gravity apply to a single star, they must apply to everything. They must apply to the biggest object in existence. They must apply to the universe itself. And this leads us to the final, most terrifying and most beautiful realization of all. The Planck star is not just a curiosity in the sky, it is the blueprint for our entire existence. Think about the biggest question humanity has ever asked. It is the question that every child asks their parents, and every philosopher asks the stars, where did we come from? The standard answer, the one you learned in school, is the Big Bang. We are told that 13.8 billion years ago, the universe suddenly appeared out of nowhere. We are told that everything, all the matter, all the energy, all of space, was compressed into a tiny, infinitely dense point. And then, for some reason, it exploded. It is a great story. But there is a flaw. A massive, glaring flaw that we have already talked about. The standard Big Bang theory starts with the singularity. It starts with that dreaded error message. It tells us that at the moment of creation, the universe had zero size and infinite density. By now, you know what that means. It means the theory is broken. It means we are missing something. In the real world, things do not appear out of nothing. Infinity is not a beginning. It is a question mark. So, let's apply the lesson of the Planck star to the birth of the cosmos. If a star cannot be crushed into a singularity because of the space pixels, then the universe cannot be crushed into a singularity either. If a collapsing star hits the floor and bounces, then maybe, just maybe, the universe bounced too. This is the theory of the Big Bounce. Loop quantum gravity suggests that the Big Bang was not the beginning of time. It was simply a transition. It suggests that before our universe there was another universe. A universe that existed before ours. A universe with stars and galaxies and maybe even life. But that universe had a destiny. It was contracting. Gravity was winning. Over billions of years, the galaxies of that previous universe were pulled together. The sky shrank. The temperature rose, the stars merged. It was the reverse of what we see today. It was the Big Crunch. Imagine standing in that previous universe. You would see the cosmos falling down on your head. You would see all the matter in existence rushing toward a single point. It would look like the ultimate apocalypse. It would look like the end of everything. And according to the old physics, it was the end. The universe would crush down to a singularity and vanish. Game over. But the Planck star saves us. Just like the star inside the black hole, the collapsing universe hit the limit. It crunched down until every galaxy, every star, and every atom was squeezed into a volume no bigger than a nutshell. It hit the quantum grid. It hit the fundamental pixels of reality. And what happened? It didn't disappear. It didn't reach zero size. It reached Planck density. The entire cosmos became one single colossal, unimaginable super-Planck star. The pressure was absolute. The energy was infinite. The fabric of space was compressed like a spring loaded with the power of a trillion suns. And then nature did what nature always does. It pushed back. The collapse stopped, the direction reversed. The big crunch instantly transformed into the big bounce. Bang! The universe exploded outward. Space expanded faster than light. The energy cooled down. Quarks became protons. Protons became atoms. Atoms became gas. Gas became stars. That explosion, that moment of rebound, that is what we call the Big Bang. This changes everything you think about your own life. You are not the result of a random accident that happened once. You are the child of a rebound. The expansion we see today, the galaxies flying apart, the universe getting bigger every second, is simply the aftershock of that bounce. We are currently living in the white hole phase of the universe. We are the explosion. But this concept unlocks a thought that is even more profound. If it bounced once, has it bounced before? If the universe works like a lung, expanding and contracting, then this might not be the first time. This could be the billionth time. We might be living in an eternal cycle, a cosmic heartbeat that never stops. Inhale, the big crunch. Exhale, the Big Bang. Inhale, exhale. This idea turns the universe into a breathing organism. It removes the need for a start and an end. There was no beginning of time. Time stretches backward forever through an infinite chain of bounces, and it stretches forward forever through an infinite chain of future universes. This answers the question, what happened before the Big Bang? The answer is the previous universe. And it answers the question, what happens after the end of the world? The answer is the next universe. This connects perfectly to the black hole theory we just learned. Remember how a black hole is a universe in a bottle, a sealed region of space that collapses and bounces? Well, our universe might just be the inside of a really big black hole. We are trapped inside our own event horizon, riding the shockwave of a bounce that started 13.8 billion years ago. And just like the Planck star inside the hole, we are expanding. We are evolving. We are processing information. And what about the information? Remember how the Planck star saves the data? Remember how the white hole spits it back out? If the big bounce is real, it means the information from the previous universe might have survived. The laws of physics, the constants of nature, the very structure of our reality, these might be the memories of the universe that died to give birth to us. We are built from the ashes of the past. We are the sequel to a story that has been told 1,000 times. But there is a haunting beauty to this. If the universe is breathing, it means it is alive in a way we never understood. It means the violence of the Big Bang was not a chaotic explosion, but a controlled, necessary biological function of the cosmos. It had to contract to be reborn. It validates the feeling that we are part of something vast and cyclical. Ancient philosophies talked about the cycles of time. They talked about destruction and rebirth. Now, loop quantum gravity is giving us the math to back it up. So look up at the night sky one last time. Look at the darkness between the stars. You are not looking at an empty void. You are looking at a fabric made of tiny weaving loops of gravity. Look at the stars. You are not just looking at burning balls of gas. You are looking at future Planck stars, future seeds that will collapse, bounce, and create their own baby universes. And look at the expansion of the galaxies. You are watching the chest of the giant rise. You are watching the cosmic exhalation. We started this video looking for a monster. We thought the black hole was a villain, but we found a savior. We found that the mechanism that creates the blackest darkness is the same mechanism that created the brightest light, the Big Bang itself. The Planck star is the key that unlocks the history of everything. It tells us that there are no singularities, there are no edges, there is no zero, there is only the bounce. We are fleeting passengers on a wave of energy that started before time began. We are the eyes of the universe, opening up for a brief moment in the middle of the expansion, trying to understand where we are. And the answer is simpler and more majestic than we ever dared to dream. We are not lost in the dark. We are not falling into a bottomless pit, and we are not the first. The story of the universe is not a straight line from start to finish. It is a circle. It is a heartbeat. It is a song that plays on loop forever. And as for us, as for you and me, sitting here on this little rock, floating in the aftermath of the explosion, we are the evidence. We are the matter that survived the crunch. We are the stardust that rode the bounce. So, the next time you feel small, remember the Planck star. Remember that deep down, at the smallest level of reality, the universe is solid. It is resilient. It refuses to be crushed into nothing. It always bounces back. And because we are part of it, so do we. We have solved the mystery of the black hole. We have found the star hidden in the dark. And in doing so, we found our own place in the eternal rhythm of the cosmos. The mystery is no longer what is inside the hole. The mystery is, what will the next universe look like? But that is a story for another time. For now, just remember the most important truth of all. The universe is not silent. If you listen closely enough to the math, you can hear it breathing. We might be living inside the echo of a bouncing star.